The purpose of this session is to try and give everyone a chance to think about the technology itself that has changed. So what I wanted to do was to go through what is currently possible to do on computers in the realm of mathematics, particularly in the realm of mathematics seen from an educational perspective. So for some of you, I'm sure you'll know all of this, but for some of you, some of these things might come as a surprise, just how automated mathematics has got. I'm not going to distinguish between computer-based and computer-assisted. I'll leave the interpretation of what to do with these tools to other sessions. And as a slight apology, it's a biased view. I've spent a couple of decades now working with Wolfram technology, so that I'm going to show everything in our technologies, but there are other technologies out there for doing many of these individual bits and pieces that I'll show. So there were thousands of bits of maths that I could show, but I thought what I would do to motivate this would be to go through some of the typical things that we're asking children to learn how to do in different parts of the curriculum. And I've very loosely broken this up into different levels of education. So the thing that perhaps doesn't come as any surprise is that we can do stuff with numbers. Calculators have been doing that since I was a child. But we work equally with all kinds of numbers now. All of these things are essentially trivial to do on the computer. So the fact that we can work with fractions is no more complicated than working with decimals. And if it's a complicated fraction, then that's equally trivial to do. We can work with complex numbers, complex fractions, real numbers, and also very high precision and exact numbers. So I stole this one from Stephen. Wolfram likes to give this as his example. We can work exactly. So if you need to know numbers precisely, that's 1989 to the power of 1989. So all of these things are essentially unlimited. All of the visualizations that we teach kids to do by hand, like graph sketching and charting, also equally automated. So here's bar charts and pictograms. And the aesthetics as well are getting much more automated so that we can have visualizations that look beautiful as well as being functional. But the visualizations also extend into all of the different ways you can look at data, the different ways you can look at expressions and models, and even things that are essentially highly education biased and nothing at all to do with the real world, like the number line that we get kids to learn their number placement with, are all just automated activities. Next one looks a bit complicated, but it's actually just a math way of writing down what's the chance of getting 12 if you throw 2 dice. And we get the kids to count through all the combinations and work out that out of all the 36 possibilities, there's only one that they add up to 12. But it gets very tedious very quickly. If you want to ask out of 20 coin tosses, what's the chance I'll get between 7 and 18 heads? That kind of thing is really computationally tedious, even though it's not that demanding. But of course, like all of these other things, these are the most trivial examples. And if I wanted to say, I know, something like I throw darts at a dartboard with a skew normal distribution in 2 dimensions and it's truncated at the edge of the dartboard, what's the probability of where I hit? It's barely any harder to ask. Okay, let's go up a little bit higher into education. And there we start getting involved in algebra and things like that. So algebra, just like numbers, is entirely automated. So I can ask questions like, what's the polynomial expansion? And we can go through those sort of binomial coefficients that we teach in school. But like all things, these things scale to, it's not very scaled, is it? Let's do 113. There we go. So all of these things just scale. And that's the power of the computer, is that while the concept is identical, the work involved is hugely different. And computers don't mind working hard. Here's one I learned at school. I was made to memorize the double angle formulas for cos and tan and sine. And I think I can remember the cos one. Somebody will correct me. Cos squared minus 1, something like that. But nobody taught me the triple angle formula, or likewise things like the 20 angle formula. I could derive this. It would take me all afternoon. I don't know if I could still do it, but certainly there was a time where I could derive these kinds of things. But we teach this little special case of the double angle formula, and yet even if you think these things are important and they're part of the curriculum, they're only still special cases of a much wider set. Likewise, we spend lots of time trying to simplify trigonometric expressions and algebra, and that's automated as well. Another classic example, another thing I learned by rote at school, although of course I usually forgot that it's only true, the quadratic formula for a not equal to 0. But again, all of these things just scale up to much larger problems. Graph sketching as well. We've spent lots of time with the most simple cases of where the x and y intercept are and drawing straight lines with linear equations, but things like this are really quite demanding to do by hand, and yet getting an appreciation is just essentially trivial. And there's a whole realm of different ways you can look at these things. So here's, for example, inequality plotting, the region which satisfies some inequality, and I guess I could make that more complicated and get something fancier. Now, of course, plotting and visualization become essentially impossible in practice to do once you get past 2 dimensions. So as soon as you start getting into things like 3-dimensional visualization, then this sort of simple branch cut of square root in the complex plane becomes pretty easy to do. But imagine trying to draw that by hand. You have to have serious artistic skills and understand perspective, as well as actually working out where all the interesting points are in the function, and maybe something a bit fancier. Similarly, with all this stuff that we do with matrices, I always have this challenge when I think about matrices of what are matrices for? I have to explain this kind of stuff to salespeople at Wolfram Research. And it's, I realize that the reason why we do rotation stuff is it's about the only thing you can do with a 2x2 matrix. So we do lots of stuff with rotations and transformations of arrows on a plane because 2x2 is within the realms of being able to do by hand. So again, I can do these things with numbers or exactly. But there are very few things that don't require kind of larger dimensions. So I was trying to think of an example to be slightly bigger than this. And I could do a 10x10 one and show you a big formula like before. But I thought I'd pick out something that was slightly more useful. So this is a thing that is face recognition, and it'll manipulate here where I can pick different people, and I can try seeing it, does the algorithm still recognize them? And what this actually here is the distance from the eigenvectors from the faces. There's 10,000 pixels in the faces, so we're doing eigenvectors of a 10,000 by 10,000 matrix in order to be able to do face recognition. It's just the same concept of eigenvectors, but it's just impossible to do these kinds of interesting things with pencil and paper size problems. Okay, let's go on to some things that you only hit in high school. As Conrad said, things like calculus we tend to save till later. Bit of red there suggesting this might go wrong. So things like fitting. I did this at my A level, and I guess I'm not getting the data here. Have I lost network? Well, maybe I'll cancel that one. I spent an afternoon doing linear regression by hand and working out all these sums of squares and so on. And let me just kill that example and see if I can fix this here quickly. Okay, well, I obviously don't have the appropriate network that I need. Let's skip that one. But one of the things that, of course, you can't do by hand is lots and lots of practice. When it takes you half an afternoon to do a single fit, then overfitting, underfitting, seeing what happens if you fit to quadratics or over 2-dimensional or 4-dimensional data is just simply out of your reach. The calculus, all automated as well, so we can do things like limits and derivatives, we can do integrals, and of course these things all scale perfectly well as well. So essentially, everything you can think of in school is covered, and conceptually, things like differential equations are no harder once you know how to write an equation and know how to describe a derivative. And things like this orbits of planets thing, we don't do this kind of stuff in school because it's too hard. I set somebody the task of going through an A-level, the kind of premier exam that UK kids do at the age of 18, and out of the entire A-level paper that he went through, every question but one could be answered by simply restating it into either mathematical or Wolfram Alpha. So we got the actual answer out in all but one, and the one hardest one, I think it took him about 3 lines, which he had to join together in order to make it answer the question. But it does, of course, if he'd done that in the actual exam, apart from if he got caught with a computer, he'd be thrown out. He wouldn't actually get the marks because, of course, we want to show working and steps. The answer isn't all of the points in the exam. But even things like that, there's progress being made on what it means to actually do maths. So here I think this is pretty much the example that Conrad showed of solving some simultaneous linear equations, and we've got a nice picture and some nice answers. But things like, well, what would I do as a student in order to solve this step by step? Well, that can all be more automated as well. This isn't how the computer does it internally, but we can simulate humans and see the steps that you would take to essentially do row reduction. in a completely step-by-step way. So if I wrote this out, apart from the illegality of the computer in the exam, it's essentially a full marks answer. Now that's not complete. There's a lot of things that's just not worth the effort, because the way computers solve certain problems is just radically different than humans, and it's essentially an exercise in showing the pointlessness of maths education in order to automate all of these things. But even that is within the scope of these systems. So, maths is automated, but that's not the whole story. Everything I've done has looked pretty verbose, because I've done it the way, if you're a programmer or a serious developer in the real world, then you want language access in order to be able to control the computer. But it's not necessarily always the way you want to do it. So we need to be able to access this power without the expertise. There's no point replacing maths, all that sort of saved maths hand calculating time, with having to learn how to use a system in order to do it for you. You're not really gaining anything immediately until you reach the outside world. So we want to be able to also enhance the access and the interfaces. And there you start hitting a challenge. You've got opposing forces of open and closed interfaces. What I've been using so far is the entirely open interface. I can say anything, I can express it all through programming languages, but there's no guidance. So I've got full creative control, but I can easily get lost. And in an educational space, sometimes we want to guide movements a little bit more. I showed a couple of apps, and they're the opposite, and they're closed. I've got two sliders, and there's no getting lost when you've got two sliders. You slide one slider, you slide the other. There's no kind of, did I make a mistake and type the wrong thing in? But there's a limit to what you can express and reach. So there's been a lot of work in exploring how these two opposing forces can be meshed. And I'll show a few sort of different slices on the same issue. So one is to keep the completely open-ended, but to help. And I'm just going to drop out of the presentation mode here into a kind of more working environment, and into the system. And in this working environment, I've got this sort of helpful assistant. This is the Clippy saying, are you trying to write a letter? But in maths, of course, we don't have that fuzzy linguistic problem of trying to decide, are you really writing a letter because it started, Dear John? We've got actual semantic meaning, so out of this piece of input, I can immediately get a bunch of suggestions that, well, I might want to see what that expression looks like plotted. It's a polynomial, so maybe I'd want to expand it, or I'd take the derivative or integral. There's a whole bunch more relevant things here, and if I sort of work through this, do the integral of it, and then maybe expand that, and then maybe plot that, and now we're in a sort of different space, and because I've got a plot, it might say, well, maybe you want to change the look of the plot. I might want to turn the frame into, I already was in a black frame. Let's say some ugly background here, put it in grey. So there's a lot you can do with contextual help, and in fact, the context can go back not just to what kind of expression we're holding now, but it knows my entire history. So it knows if I started with some random numbers, well, maybe I'm doing something more statistical than I am, I'm doing something in Monte Carlo, so it'll offer up things like statistics options more than it will offer up data counting options, perhaps. Another is automation, and there's different slices on automation. One of those is automation of application. Sometimes we want to do something, but we don't really care about the steps. And in a sense, all of this automation of the mathematical computation is doing that. But the same thing is being gradually extended into knowledge as well. So I can use the solve command we've already seen to take Ohm's law and put in 30 amps and 5 ohms and solve it for voltage. But I don't need to do all of that, because that can be automatically looked up what Ohm's law is, and so I can simply give it the values here and have it figure out, well, Ohm's law is VIR, that's because of the units these are in, it can figure out which parameter I'm talking about and put those things in. Or something for sort of more classical school education, I can give a triangle, and it knows M is probably meters, so it can interpret that, and hopefully, I've got a solution here. It can tell me some interesting facts about this triangle that I've just described, like the kinds of things you would have to solve using the sine rule, or the sine rule would be the useful one here. So we can start combining the knowledge of what you would need to know to be able to use it with the maths of doing it. And so this sort of level of automation is sort of creeping down the knowledge chain. And it also gets into the idea of expertise. So here's another example that I spent time studying, and this is not going to work because I don't have the data connection. Oh, no, I do have it now. So here I've taken some data. This is sizes of some crabs, some built-in data set I've got, and I've asked the question, I believe crabs are 12.5 centimeters wide. Does this data support that? And it said yes, at the standards of test level. The t-test student t-test that I spent lots of time looking up in tables, tells me that, yes, this is plausible. So I'm going to do the same thing here now with airline passenger miles. And it's exactly the same concept, exactly the same kind of answer, but there's a little subtle change here. Anyone know the reason why? No maths person? Well, there goes to show the importance of this kind of automation. What I'd long since forgotten if I was ever told is student t-test only applies if the data is normally distributed. Turns out this airline data isn't normally distributed. If I force it to try and do a t-test, it'll tell me that. I've looked at the data, it's not normally distributed, so the sign test is more appropriate, which is why this came back with the same kind of answer in the sign test. Throughout mathematics, there are all these little corners and things to worry about. There are 30 different ways to solve numerical differential equations built into Mathematica, and I have no idea when to use Runge-Kutta or Adams' method, or which is the right thing for a partial differential equation compared to a differential algebraic equation. And that kind of automation becomes much more important if we want to focus on, I've got a differential equation, I want to see the answer. And I don't need to worry about all these pitfalls and special cases that the various algorithms apply to. Well, this comes back to Conrad's comment about the mechanics of the day. Some of these things aren't automated, and it is very important to know the corner cases. But if they're automated, then surely that allows us more just to move on and focus now on the more complicated questions we could be asking, rather than spending all of our time going through the details of the algorithm and deciding whether or not I'm going to get caught by something. We do need to know where we're going to get caught, where they're not automated. But in the long run, that's going to drift further and further into the obscure. So still on the open end, we've got linguistics. And I can start asking questions now in a very fuzzy linguistic ways. But you're starting to now pay a price that we don't have the preciseness of programming languages, where we get something that I guess I had a simpler example when I was practicing. That was going to give me a nice simple formula, and we got something in terms of root objects. But the fact that I can specify this problem and not have to worry about the fact that the Mathematica command is maximize and how to bracketize the sign and its arguments, that can be automated. And again, lets us jump straight into doing something without having to spend the time on syntax. And perhaps less usefully, and probably a lot further off on the horizon, there is progress in natural language processing to be able to do things like take this sort of primary school word problem and strip out of that some notion of verbs and adjectives and values and get answers back from sort of classical school word problems. I think it's a long time till that's going to reach a very rich level, but for the kind of simple things we're asking kids to do, it's already becoming possible. And then as we get more towards the close, there are all kinds of GUI technologies out there, sometimes specialized things like drawing circuit diagrams, sometimes more interactive, more self-contained things like interactive interfaces. And I'm overrunning here. So let me just say a few words before I pass on to somebody else. There are also issues to do with how we share maths. What are actually the deployments? So we've seen coding and doing stuff live. We've seen things that are self-contained where stuff's hidden. Here's one I wrote a couple of weeks ago for a blog next week, which is playing classic rock, paper, scissors. We don't really have to see anything to do with the maths here. The maths isn't actually the charts. The maths is the hypothesis tests and partial probabilities behind the scenes. But it can all be encapsulated so you can access it without having to deal with things. And we have a website which you can browse at your leisure where there's something like 9,000 of these kinds of pre-built things to illustrate particular ideas where maths can be entirely packaged away. But part of that is also not just being apps, but documents. Here's a document that was presented to House Committee on Insurance, and it's mixing narrative and interactive mathematical content. And of course, that's particularly important in things like the textbook space where here's a sort of very classical calculus textbook, but everything that's in it is interactive and automated. We can click on these things and see the diagrams update. But part of deployment as well, and particularly as we talk about developing countries, is the hardware deployment. And I started using Mathematica on one of these $4,000 bad boys, and for a long time, this kind of computation was purely the realm of those with proper professional computers. You've seen Conrad already using mobile phones, and we're working on things like iPad versions of the technology that will run natively. But there's also the change, of course, and perhaps I can invite Eben to come up here and take over, who knows much more about this than I do. The non-traditional computing platforms that are emerging like systems on a chip, like the Raspberry Pi. So if I can hand over to Eben, who's the CEO of the Raspberry Pi company and founder of the Raspberry Pi Foundation, and he knows a little bit more about this than I do.